Have you ever wondered what would happen if the speed of light suddenly changed, or if gravity was a little stronger or a little weaker? Our universe is built on a set of immutable rules and numbers known as physical constants. They are the solid foundation for everything we know, from the formation of stars to our very existence. But are these constants truly immutable? Or are we just living in a universe with lucky parameters perfectly tuned for life? In today's video, we will explore one of the deepest mysteries of the universe: physical constants. Can we change them? Or are we merely products of them? Welcome to SpaceTime's journey of cosmic exploration, where we uncover the deepest mysteries of the universe. In this video, we will delve into the topic, physical constants. Can we change them? Don't forget to subscribe to the channel so you don't miss other exciting cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us.
Physical constants are fixed values that do not change with time or position in the universe, and they play an extremely important role in shaping the laws of physics. Typical examples include the speed of light, c, the gravitational constant, g, Planck's constant, h, the elementary charge, E, and the proton-electron mass ratio. Within the framework of our current understanding of physics, these constants are considered fundamental elements that cannot be derived from any deeper principles. We can only measure them through precise experiments, and they are the foundation for cosmic models from the dawn of time to the present day. However, the most astonishing thing about physical constants is their incredible fine-tuning. If any of these constants were to change even slightly, by as little as 1 part in a trillion, the universe as we know it would likely not exist, or at least would be unable to support life. For example, if the gravitational constant, g, were slightly larger, stars would burn faster, and the universe's lifespan wouldn't be long enough for complex life to form. Conversely, if it were weaker, galaxies and stars wouldn't be able to condense, leaving an empty and cold universe.
The fine structure constant, alpha, which governs the strength of the electromagnetic force, is also a clear example. If alpha were larger, atomic nuclei would be unstable. If it were smaller, electrons would not be bound to nuclei, preventing atoms from forming. Furthermore, the proton-electron mass ratio is a crucial factor for organic chemistry. This delicate balance allows complex molecules to form, which is a prerequisite for the emergence of carbon-based life. Even the cosmological constant, a quantity related to vacuum energy and the expansion of the universe, must have an incredibly small and positive value. If it were slightly larger, the expansion would be too rapid, preventing any structures from forming. If it were a large negative value, the universe would collapse immediately. Faced with this extraordinary fine-tuning, scientists have proposed many hypotheses, among which the Anthropic Principle stands out. This principle seeks to explain why the constants appear to be just right for life. The weak Anthropic Principle states that we observe a universe with constants suitable for life because we are conscious beings who can only exist in such a universe. In other words, if the constants were different, there would be no one there to observe.
The strong Anthropic Principle goes further, suggesting that the universe must have properties that allow life to develop at some point. However, this hypothesis is less accepted in scientific circles because it is philosophical and less verifiable. A proposed scientific solution to the fine-tuning problem is the multiverse hypothesis. According to this hypothesis, there are countless parallel universes, each with a different set of physical constants. In this scenario, our existence in a universe with constants suitable for life is no longer a random stroke of luck, but a statistical inevitability. It's like being certain to find a blue candy if there are enough different kinds of candy. Some modern physical theories, such as string theory and M-theory, offer potential mechanisms for the existence of a multiverse and the variation of constants. In these theories, constants might be determined by the shape of extra spatial dimensions. Different compactifications of these extra spatial dimensions in various regions of the multiverse could lead to different constant values. Scalar fields, also known as moduli fields, might also influence the constants. Scientists have been conducting many extremely sensitive experiments to search for evidence of changes in physical constants over time or space. So far, all evidence indicates that they are immutable.
For instance, analyzing light from distant quasars, which has taken billions of years to reach Earth, allows us to test the value of the fine structure constant in the universe's distant past. The results show no significant change. Even studies of the natural nuclear reactor at Oklo in Gabon, which operated 2 billion years ago, provide tight constraints on the variability of nuclear constants. If physical constants truly changed, even slightly, the foundations of modern physics would crumble. Our cosmic models, from general relativity to the Standard Model, all rely on their invariance. The search for a theory of everything is a major goal of physics, one that Stephen Hawking pursued throughout his life. Such a theory could explain why constants have the specific values we observe instead of treating them as arbitrary inputs. Quantum mechanics and quantum gravity are also promising areas for deeper exploration into the nature of constants. A unification between these two theories could open new doors for our understanding. Some physicists also question whether constants are truly fundamental or merely emergent properties from a deeper reality, much like pressure and temperature are emergent properties of molecular motion. Regardless of the answer, the existence of physical constants with such specific values is one of the deepest and most captivating mysteries of the universe, challenging us to explore the limits of human understanding. Carl Sagan once spoke of the grandeur and beauty of the laws of the universe. Physical constants are the notes that form that grand symphony, allowing everything, from fundamental particles to colossal galaxies, to exist and interact harmoniously. The limits of our current understanding of physical constants remind us of our humility before the cosmos. We still have much to discover and learn, and each answer opens up deeper questions.
The fact that these constants determine the balance between the fundamental forces, strong, weak, electromagnetic, and gravitational, is miraculous. A slight change would disrupt this balance, making the universe an entirely different place. Without these constants, there would be no stable atoms, no chemical reactions, and, of course, no life. They are the secret formulas the universe used to create itself. From the Big Bang, physical constants have governed everything: the expansion rate, the formation of particles, the first atoms, and ultimately, stars, galaxies, and planets. The cosmological constant problem, also known as the vacuum energy problem, is one of the biggest challenges in physics. Its measured value is vastly smaller than theoretical predictions, creating a major cosmological constant problem. The holographic principle in theoretical physics suggests that the information of a 3D space can be encoded on a 2D surface. Could this imply that our constants are emergent properties of a more fundamental reality? The Standard Model of particle physics has many free parameters, which are constants whose values are not explained by the theory itself. This is a significant gap that physicists are trying to fill.
Are there other fundamental constants that we haven't discovered yet? Or could some existing constants be derived from other, simpler ones, if we had a unified theory? The ultimate question remains, is our universe truly unique in its physical laws and constants? Or are we just one among countless infinite possibilities? The mystery of physical constants is not just a scientific challenge, but also an invitation. An invitation for us to look deeper into the nature of reality, to ask big questions, and to seek answers that could change how we perceive the universe forever. The mysteries of physical constants have led us to the boundaries of understanding the vast universe. But as we narrow our focus to the smallest scale, the world of particles and strings opens up even stranger things, challenging our intuition. In the next video, we will delve into the surreal world of particles and strings to explore quantum mechanics, the surreal world of particles and strings. Don't miss it.